Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. Now, what you're about to see is a pre-recorded training session we did over in the United States. But be assured that a lot of the material that we cover is really applicable to any automotive application. So just be aware that yes, it is a lot of North American vehicles, but a lot of the same principles apply over in the UK as well. Now, if you have any questions, if you're watching this during the premiere, you can just leave it in the chat. We'll be monitoring that. And if you're watching this after the premiere, then just feel free to leave a comment underneath the video, and we'll get to those as we can as well. So my name is Jason Gabrenas. I'm one of Snap-on Diagnostics technical trainers. I've been in the training department since 2013, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep at Snap-on, so I had a group of about 30 different franchisees I worked with, as well as the shops that they service, in order to help everyone get the most out of their diagnostic needs. Then before I did that, it was 8 years at Subaru, so I worked in a dealership, and over time, I guess, I just became that default diag guy in the shop. So I always ended up having the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that had come into my bay. Then before that, a bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. So our topic today, we are going to dive into the scanner versus scope. So they are different tools for different jobs, and we're going to talk about how one might be used for one thing, one might be used for another thing, and how they might complement each other as well. So if we think about our two main diagnostic tools, there's others, of course, but scanners and scopes seem to be the ones that get used the most. Scanners are, I like to think of as a really nice compass. It's going to point you in the right direction. It's going to show you where you need to look, where you need to go. But it's only showing you part of the equation. It's only showing you the effect. Like after everything happens, that's when you're going to see it come out of the scanner, right? After it's already in the past. Now, in order for every effect, we have a cause, right? So we're going to find that cause. That's where the scope is going to come in. If we think about, they're good at different things. Scanner's good at any stuff that I have to do with controlling the computer, bidirectional controls, things of that nature. And then scopes are really good at looking at raw data. So if we think about a vehicle's computer, when we're testing, especially for, say, a drivability problem, vehicle's computer operates, let's think of it like a house. It's got a front door and it's got a back door. Now, coming in that front door is going to be all my data inputs. So it's going to be my oxygen sensor, my NOx sensor, my coolant temp sensor. All of those things are going to go into the computer. The computer is then going to process it however it is programmed to do so, and that's important to note as well, because it's only as good as its programming. And oh, by the way, did you know that the computer has two different sets of instructions? It has my OEM VIN-specific side of the computer, which is where the OEM, it's up to the OEM's discretion how they process data and how they determine threshold levels for codes to set. And then we have the OBD2 side of the computer, which is mandated by the government. So over here, it'd be the US or Canada government, and over in Europe, it would be like the EOBD standards that are over there. So either way, the government mandates one side of the computer versus the other. Now, if I'm looking at the information on the scan tool that comes out the back door, we think about that as the back door, right? Goes through the two rooms, gets processed, gets sent out two separate back doors. If I go in with scanner on a Snap-on scan tool, that is going to bring me into my OEM VIN specific side of the room. So it's going to be all the manufacturer data, the manufacturer test, the manufacturer codes. If I go in OBD direct, I can go into the OBD2 side only. So that is directly into the EOBD OBD2 side. Now, sometimes, most manufacturers, not all OEMs, but most manufacturers, we have ways of getting from the scanner from the OEM side through this wall over to the OBD2 side while we're still in scanner. And I'll show you a couple instances of that in a little bit. But it is important to check both sides, and it is also important to check the front and the back. If I'm only looking at data, I'm only looking at codes, and I don't bother testing the stuff that's coming in, I'm doing myself a disservice, and I might misdiagnose a vehicle. Yeah, maybe you might be able to diagnose it somewhat using the scanner side, but I won't be able to verify with 100% certainty where I think the problem is unless I check the input side too. Ever heard of the term garbage in, garbage out? If I have bad signals coming in, I'm going to have bad signals coming out. But what if I have bad signals coming out because the computer has some sort of problem inside, and then my data input is good, and then I end up replacing whatever component that was that I suspected was bad, but it's not bad because I didn't do my due diligence and check in here, right? So it's always very important to check and make sure the data coming in matches the data coming out. And there will be a little bit of a lag. We'll see that here in a minute. And you will see that you will definitely get more detail by using a scope. But horses for courses, as we say, the right tool for the job. Scan tool, what can we do with the scan tool? Well, almost always we'll do a pre-scan, right? Pre and post scan on a vehicle, check for codes. That's the right thing to do, just to see if there are any codes in other modules, or are there any codes that kind of go with each other. So we can definitely get codes with that. Process data, as I said, any of that output data that's coming out of the computer, we'll be able to see that. Functional tests, of course, bidirectional controls, where I take over the computer and tell it to do something, override the modules inside the computer and tell, oh, turn that thing on, even though you don't want to turn it on. I'm going to tell you to turn it on anyways, like a solenoid or something like that. Resets, relearns, programming, coding, all of those things would be done with a scan tool. They would not be done with a scope. However, if I want to test anything coming into the computer, like I said, voltage for one thing, I can test and make sure the circuit is working, verify that it's outputting the proper voltage, make sure I don't have any opens or shorts. I want to check current. I want to see how is this thing working using the electricity that it's being provided, using the current flow. Pressure, by using a pressure transducer, I can see, drop in liquid pressure, fuel pressure. Check, compression, that sort of thing, running compression. All sorts of different things we can do with pressure. Transmission line pressure if you're a transmission person, right? Resistance. Maybe I want to be able to see a visual of what's going on resistance-wise in a circuit. I know I've talked to quite a few like transmission shops in the day that they say, hey, I'd like to be able to graph the resistance of this. Usually it's a transmission temperature, trans-temp sensor. There we go, transmission fluid temperature sensor. That's what I meant. Over time, because as it goes, the resistance will change, and that'll change the output voltage. And sometimes they have an issue inside, and at some point the resistance drops or raises or what have you, as it should just be a linear curve. And then temperature. There are temperature probes that can be used with a scope as well. There's a couple that we have that are available that you can graph temperature, different temperatures and inlet and outlet of your radiator, or lots of different things we could do with that. Different cylinder head temperatures, in between cylinder temperatures. One's hotter than the other, could be. Plenty of different things we can do with that and graph it. And you may be saying, well, why don't I just rely on the data anyways? It's what we do. We look at the data, but it's not always, as I said, it can't always necessarily be 100% accurate because of too many variables in what can go wrong with a computer. So I got my inputs and I got my outputs. Data is an output, if you think about it. It's not an input. It doesn't go into the computer. It doesn't really factor into any of its decisions. It's from external sources, and then it factors in. There are some things that get figured out within the computer based on its data inputs that it has, like misfire counts and AF sensor things, voltages and things like that get figured out by the computer. But it's only one piece of the puzzle. And I don't know about you, but if I'm looking at data like this with numbers on the screen, modern vehicles, those numbers are changing pretty darn fast. And they can be changing 10 times a second or faster. And I don't know about you, but I have trouble reading things when they're changing 10 times a second. It is good data. It's valuable data anyways. It's good to have, but it's too fast and there's often too much. I've been on vehicles with over 400 PIDs you have to choose through in order to get the data that you need. With our tools, of course, we have fast track intelligent diagnostics and the custom data lists and things of that nature, which help bring that down to a more manageable level. But it's like data overload nowadays. And then, of course, pretty much any scan tool out there on the market nowadays is going to have the ability to graph that data. And that graph that you're seeing on the screen is going to be a recorded history of those numbers that are plotted over time by that processed data coming out the back of the PCM. Once again, it's processed data. It's not live. There's always going to be a lag. You can see trends, whether things are getting better, getting worse, or just completely not there. And like I said, there are some things that get figured out internally. But due to the sample rate of what can happen in the computer versus what's actually being fed to the computer through the raw data inputs, it's different. Computer has to take a sample of the data whatever sample rate it has, takes a sample of the data, and then it processes it, and then it sends that data out to the scan tool as an output. So every time it does that, you lose a little bit of resolution in the signal. So you will see a difference in the data capture signal. And it's not the scan tool's fault. It's just by design how the computer works. The computer takes a sample of the data, processes it, sends it to the scan tool. Some vehicles, it can be quite fast, but there's still going to be that lag, and it's still, once again, an interpretation of what you see versus what the inputs are. So the difference is really in the details. If you look at these two screens, the top part, that is going to be oxygen sensor voltage, reading process data coming out of the OBD2 port. And then this part of the screen is going to be a scope hooked up to the same oxygen sensor, reading the same values, same voltage values anyways, coming out. And I think you can agree, these two red boxes, which show the same amount of time passing, these two red boxes, those patterns look completely different. Now, the values might end up being the same somewhere up here, up on top or whatever, but the computer wasn't fast enough to catch these little drops right here. Now, whether or not it be a glitch or not, or maybe it's just a quick dropout for whatever reason, it's not able to show you that because of the processing speed. Now, here's another one that I just captured yesterday. So this is a mass airflow sensor. I just wanted to show the example of this. So the mass airflow sensor here reading voltage. And on the right-hand side is connected to the mass airflow signal wire and reading them at the same time. This is just a screen recording of my tool. And what we're going to see is a couple things. One thing I want you to note is that because the tool auto scales, this looks like a lot, but it's only 0.2 of a volt. We got 1.3, we got 1.4, we got 1.5. That's it. 0.2 of a volt right there. That's not very huge in the whole grand scheme of things. So we can see down here that we're about a little under 1.5 volts. So that'd be your 1.3 volts down here. It's probably about 1.3, give or take right there. Now I'm going to press play on the video and you'll see what happens to the data graph over here versus the real-time data coming out of the actual mass airflow sensor. So you can see it go. And the AC compressor was cycling periodically, so you're going to see that kind of go up and down. But then I decided to do a brake torque. And there's one rev there. There's another rev there where I held it a little longer. And then there's another one there where I held it a little longer still. And you can see there's a lot of hash going on there. And you can see that the data over here did not react nearly as fast. So if I was looking for something like that, the noise and whatnot, and let me just get you to a still picture here. I zoomed in on the scanner data a little bit more so you can kind of see what's going on. But it only picked up on a couple of those, and it wasn't a big difference. So the max on this says 2.6, which is where we're at right there. That's the very top of that peak. Versus the max I see over here is 2.89. So it wasn't even able to catch up on it. It was like stuff over here, or maybe it was on this one that picked up on the max, right? So big difference in the detail, and you also see a bit of hash going on there. So if I was looking for that in particular on whatever component I was looking on, that would definitely be missed with looking at the process data coming out of the computer. So that's why we definitely need to verify operation, verify our inputs are good, because we can't always just rely on that scanner data. Now, what is a scope at its basic? A scope is just a window. Going to look at a window, and it's going to have a measurement in the vertical axis over time, which is in the horizontal axis. So my vertical is going to be my volts, my current, my pressure, whatever it happens to be on this value. And then over a period of time, what's it doing? Is it going higher? Is it going lower? Is it staying the same? What's the value over however much time I'm looking at? So depending on what the component is, the time is going to obviously vary, and the voltage is obviously going to vary. But when I'm changing those values in the scope itself, I'm not going to affect the pattern in any way. I'm not going to hurt the car. I'm not going to hurt the component. I'm just going to change how I'm viewing it. Do I see more of it on the screen? Do I see less of it on the screen? Do I have the top cut off, or do I have a lot of extra headroom up on top? That sort of thing. So when you're messing around with the scope, you're not going to break anything. Don't worry about that. And then, of course, if you have guided component testing, it's going to do all that work for you. You really just got to plug it in. So there's a couple of things we can do, and we can actually compare a couple of these things too. For example, injector poles. Injector poles is almost certainly going to have a matching PID that goes in the car. But if I use a scope to check an injector, I can check it in three ways. I can check the circuitry, which is going to be the yellow line, so that'd be the voltage. I can check the actual physical work that's being done by the injector, the motion of the injector, by looking at the current flowing through it, so the current ramp. And then I can also look at the fuel going through the injector by watching the pressure drop off as it opens. So if I were to look at a scan tool and I looked at the data PID for the injector pulse, that is an output, right? That's a command. Is the computer saying I'm commanding it to open for XYZ length? So we could actually compare that with what we see on the screen here. So I could put my cursors in, and I'm going to show you an example on the next screen. I put my cursors there, and that'll show me the commanded output of the actual computer that's sending to the injector to open. Now, we're not going to take a terribly deep dive in here because we've got plenty of other material that covers this. But if you look right here on the current ramp, that's the pintle leaving the seat, and that's the injector opening. And then that's the injector closing over there on the voltage because it gives it a little extra bump when it closes. Right? So we can see those actual opening and closing. And they might be a little bit different. They might be a little bit different from what the command is versus what's actually going on. Because remember, there's also that lag. Not only is it a lag in processing power, it has to figure out, okay, based on these inputs, what do I need to pulse the injector the next time it pulses? So really, it's an educated guess as to what it thinks it should pulse it at. So if we take a look at this screen, oh, never mind. Hold on a second. Let me talk through the blue line too. So we talked about the yellow line is the voltage. That's verifying the circuit is working. The green line is making sure that the injector is actually opening. That's the current. And then we can also see and make sure there's no problems in the windings. And then we can also see the pressure going through. So you see around 35 PSI here, give or take. It's pretty close. 35 and a couple tenths on either side. And then when it does open, we see it drop off. It doesn't drop off much. That's not a huge drop, just a couple PSI at most. But when it closes, what's kind of interesting is when that injector actually snaps shut, I see a pressure spike. Now, why would I see a pressure spike? Well, all that gasoline or diesel would work the same way. All that fuel is heading through there, and all of a sudden it just hits a wall because that injector closes and it closes the pintle, and there's nowhere for it to go except backwards. So the stuff that was already coming in goes in, and plus the stuff that was already in there goes in. So we get a little bit of a pressure spike. Of course, it all gets bled off back into the system and everything like that. But it's just kind of interesting that you would see it's only a couple PSI once again going up. And then you see it levels off and normalizes again and comes back. And next time it fires, the same deal. So on this next screen, this is, once again, fuel injector pulse width, which is an output commanded on time. And we see 333 right there. Once again, the AC compressor is cutting in and out a little bit so we can see the different. And once again, it's not huge. 333 there. It's probably 275 there. So maybe half a millisecond. Not a huge lift there. But if I look at this particular point right there, 333, and this is where I just paused took a freeze frame out of the video I took. There is the pulse width there, and if I measure it, look at that, 333. So they match. They should match, at least pretty close. Like I said, there's going to be that lag, but at any given time on a steady state, what's it asking for? This should normalize and steady out as well. So we're able to compare that side by side. Every once in a while, it'll move a little bit in and out. The injector will move a little bit in and out. And that's going to be normal. Every time it fires, it's going to be a little bit longer, a little bit shorter. But as long as we're fairly close, like I said, it's an educated guess of the computer as to what it needs to pulse it at. Versus the opening is going to be a little bit different. How about a timing issue? This is a pretty popular test that a lot of folks will do with a scope, and it's not that easy to check it with a scanner. There are a couple brands out there that have an automated test. BMW comes to mind, automated timing chain wear test, basically is what it is. And it checks basically where these signals fall and makes sure they're correct. And then if not, it judges whether or not the timing chain may be stretched or jumped a tooth or whatever. So in this case, I have 3 channels. I have channel 1 is the crank sensor. That's the yellow. The green is one cam sensor. The blue is another cam sensor. So this one has 2 cam sensors. And for all intents and purposes, this pattern is a good pattern. So these are supposed to line up within this window. And they all do. And when the cam sensors are aligned, they're supposed to line up with each other as well. There's going to be gaps where they're not firing at the same time. or they're not triggering at the same time, like over here, and over here. But they do line up 2 ticks out of the possible combinations. So in this case, I'd be looking at it and nothing's wrong. However, if I were to see it and say this green one is shifted over to the left a little bit, that means the timing is now retarded on that one, because it's not, everything else is lined up and this is happening later in the game. So that means it's retarded timing. Other side of the coin, I go the other way, shifted a couple teeth that way. Now it's advanced timing. So it's happening earlier than it's supposed to happen. Not every manufacturer publishes the specs as to where it's supposed to line up. Some do, some don't. It's nice when they do, for sure. But you would be able to see that with a scope and not necessarily be able to see that using a scan tool. Like I said, some manufacturers might have a test for it, but they're pretty few and far between. How about ignition? You can tell a lot about what's going on inside an engine by looking at the ignition pattern. Here's an example of a known good cranking test. So we can see all of the firing lines are fairly level with each other. There's going to be a little bit of variation, but they're fairly close. They're within, maybe a couple kV or so. It's not too bad. It looks pretty good. And then here's that same engine before we did a tune-up on it, with one plug not replaced yet. We replaced the other 3, but that one plug is not replaced yet. So now we can see how it has a much higher firing line. Now, why does it have a much higher firing line? Because it has worn out plug, and the worn out plug has a larger gap, and that gap is going to take more voltage to go across and cover that ground. So once they were all replaced, we go backwards and we see that, right? Can also tell by looking at the spark line. This is a slightly different vehicle, but we have the firing line there, and then we're looking at the spark line. We want to see it fairly flat. We want to see a little bit of turbulence in there. That means it is burning properly. Next thing we did is lean it out a little bit, pinched off the hose going to the fuel line. And now we see, okay, it was flat, it was burning good, and then all of a sudden it ran out of fuel. And when the mixture goes lean, the spark line goes up. Same thing with the firing line too. But we can see it kind of got a little wobbly there at the end too. It was almost ready to stall. I pinched it off a little too much, but nice and level coming out, and then it goes up. That is lean. Goes high and then nose dives. That would be rich, or maybe it just stays low. Kind of goes down in that way. That'd be rich. Up is lean, down is rich. Fuel pump current ramp. This is another really good test to do because you don't have to disassemble things. You don't have to take the fuel pump out. You don't have to drain the tank. You don't have to do any of that nonsense. You maybe just have to pull a fuse, put a jumper in, pull a relay, put a jumper in, something like that. Somewhere in the circuit, you want to put a lamp probe. And you want to take a look at the condition of the commutators and the brushes inside that fuel pump motor. Now, on a brushless fuel pump, it's going to be different. You can still do this test, but it's going to look different in there. And you're not going to be looking at the brushes. You're going to be looking at the pulse width signal. But anyways, like I said, other videos on these topics. I wanted to do this on my car because I'd done this on my car since it was 100 miles old up until now. It's got like 194,000, I believe, on it now. Still running strong. Still on the original fuel pump. So I wanted to see the condition of those segments in that fuel pump, and they look pretty good. They're a little more round than they used to be, which is showing signs of age. They were a lot more kind of more shark finny a little before. When I think it was like at 79,000 miles, I think was the last the first time I did it for reals. But if we can see, or took a capture of it anyway. But we can see they're fairly rounded. There aren't any missing. They're all pretty level. The current demand is going to be different depending on how much fuel's in the tank. And this was just at idle. I captured the other one at idle too. But I wanted to see, is it running in roughly the same speed? Is it slowing down? And I found it's slowing down. So I know it's an 8-segment commutator. So I have 1, 2, 3, 4, 5, 6, 7, 8. And then there's segment number 1 again. If I take that distance, I look at 7.57 milliseconds. So let's do a little math. Was it 7.57? This is now turning at 7,900 RPM. Pretty darn close. Actually, it's about 1,000 less than what it used to be on my previous slide that I used to use for this topic. It was about 8,900 RPM before. So slowing down a little bit in its old age. This is at an idle. They're both at an idle, just warmed up, full idle. But looks good still. Still looks in good shape. Nothing missing. Everything's fairly even. Everything's fairly well spaced. Not making any noise. So we're status quo. We're looking good. Another one I see a lot of questions out on about there is running compression tests. So running compression tests, you would put a pressure transducer in a cylinder and crank the vehicle over and let it run. This is at idle. And what we're going to see is we're going to see the various strokes of the engine. So here is my compression stroke coming up, coming up, coming up, coming up. And then we have ignition here, usually a little bit before the top dead center. And then we have the power stroke, comes down. We should see a vacuum pocket down here because it is drawing a vacuum with both of all the valves closed. Should be drawing a bit of a vacuum down there. And then the exhaust valves will open, and then I will have an exhaust pulse here. Now, in this case, this is a 4-cylinder engine, so I can actually see 3 other pulses in there for the engine. We don't want to ever see the exhaust pulse go above 0. If it goes above 0, that means it's having a hard time getting out, which means we have a clog somewhere in the exhaust system. Or maybe the valves aren't opening properly. That could be too, I suppose, but you might be able to see that other way. And then we have the little bit of overlap here on the intake stroke, and then the intake comes down. We should see pretty close to level on the 2 sides of that pocket, and then it's going to go back up and do it again. Now, I wanted to check it out on my vehicle. I did this probably a couple of years ago now, I think, and you should not do this on a customer's vehicle because you risk damaging the cylinder, but I wanted to see what happened. This is on my car, so it's okay. I have the pressure. I have, this is my ignition right there. So that is at the end of this would be where my ignition would fire. And then I have my fuel injector here. So compression goes up, fires a couple degrees before top dead center, comes down. We have exhaust, and then all of a sudden my injector fired. So on the previous screen, I had the injector off and it didn't fire. It was unplugged because that's what you're supposed to do. But I want to see the difference. So here we have the injector firing. As we know, that's the end of the firing roughly there. So it's coming into the intake. As it goes in the intake, you see the pattern looks a little bit different. And I got my valve overlap in there. Then it comes to the intake, and then I got my vacuum pocket there. And then it goes back up, and then it fires again. Right. So there's one cycle through that engine. So you'd be able to see valve issues, exhaust issues. You'd be able to see, make sure there's no vacuum is correct and all that. And it depends on the valve overlap and a bunch of other stuff. There's more information on how to interpret this than just this high level overview, but it's another test that could be done with that. And you're not going to be able to do that with a scope now, however, or a scanner. However, I know some Fords, for example, have an automated relative compression test. So it'll crank over the engine for a period of time, and based on the rotational speed of the engine and the cams, it will detect whether or not there may be a compression issue in the vehicle. So you can do that with a scanner. You can verify it with this, especially if you suspect there's a mechanical issue. All right, let's go live real quick. On here, on there, on everywhere. Oops. First thing I want to do is I just want to show you the what I was talking about before with the going onto both sides of the computer. I'll pull up a Camry here. And like I said, 2 ways to do it. So if we go into the engine, for example, and we go over here, we see codes, data, and then over on here, we see generic functions. So if you see generic functions inside an ECM on a vehicle, that allows you to flip over, and that sees my readiness mode, or my OBD2 mode. I got readiness monitors, freeze frame, mode 3, mode 4, mode 6, 8, 9, no mode 10. So you got a bunch of mode 9s. And then you have most of the modes, but not all the modes, right? So sometimes you have to go in a little bit deeper to find that. You might have to flip over to OBD2 to find it, but this is the majority of the information. Also, how we can do it is if we do a code scan on a vehicle. We can come in here, and we'll see I got codes here. Now it says engine codes. That means that is the OEM manufacturer-specific code. They could be the same number as the generic codes, but these are coming from the manufacturer side of the computer engine. I scroll down, however, On Snap-on Scan Tools, we also scan Mode 3 and Mode 10. So we can check the codes that are there already, and then we can also check permanent codes, which is helpful. That's on 2010 and newer vehicles. And then down here, we can see what readiness monitors are complete. So if I have an emissions test that needs to get done, or really it's just a good practice anyways to verify that they're done. Some monitors take a little longer than others, but if it's a bunch of, if it's like a 2-trip, and I haven't made 2 trips yet, you might want to make 2 trips just to make sure it sets, and then you can be more sure that that vehicle is not going to come back for the same problem. Like if I'm trying to diagnose a misfire problem, and it was a misfire code, but my my catalyst hadn't set yet, okay, then it's probably okay if it was fine before, right? So you can just kind of make a call, but I would strongly suggest having them all set before you go. Also on here, one last thing, is if from this code scan, if I wanted to just flip into the engine, I can just click the word engine, and it brings me in there. I can go to my generic functions that way. Now, what if I wanted to look at both things at the 2 things at the same time? I say both things, but 2 things at the same time on the screen. So I'm going to pull up this focus here. And let's say I go to the engine and I want to look at data, and I want to look at, let's say, oxygen sensor. So I can come in here and see, there's my heaters, I guess. Or maybe I want to look at, say, a map sensor, right? Map sensor instead. Oh, wait, no. Never mind. I remember the one I wanted to look at. It's the engine coolant temperature sensor, because in this case, on the simulator, it is showing negative 38 degrees outside. And what if it's not negative 38 degrees outside? What if it's like 62 degrees Fahrenheit like it is in my house right now? So that's obviously a problem. But is it a problem at the sensor, or is it a problem in the data? So we could go over here. Well, let's just pull that up in a graph, I guess, make it easier. Come over here, go into my guided component test. And in this case, we'll just pull up a, not that one. Oh, geez. What did I do? I went back too far. All right. Let's just call it, maybe it's an SC. There we go, the 1-liter engine. That's the one I was looking for. Go in here, and we should have, shows I didn't look. All right. So we'll go to the cylinder head temperature sensor in this case. Oh, engine coolant temperature sensor. What am I looking for a coolant sensor for? Engine coolant temperature sensor. It's in there. All right. DC voltage test. And we see connect to the signal, connect to the ground. So signal is going to be on number 2, right? So we see number 1 is the coolant temperature itself, and then the signal return in the engine. That's the one we want to look at. And then it gives us a little chart right here in Fahrenheit to volts. And then if we hit view meter, it is going to give us our little, in this case, it opens up DC volts meter. So if I see 1.299 volts, that should be around about 140, 150 degrees, I guess, somewhere in there, right? But I did not see that on the other side. So let's come over here, pull out my scanner. There's my graph. Let's make it full screen. Pull up my scope that I just had. And then I can look at it over here versus this over here. And I can see 1.299 volts there, which equals not negative 38 degrees Fahrenheit. So negative 38 degrees Fahrenheit would actually be like pegged high, right? Should be way high. Well, maybe not that high, but it would be pegged high on that, because high is low temperature, right? So it should be at probably like 5 volts. I don't know why this one's overvolting, but it'd be over 5 volts in that case, or 5 volts. That's usually where it fails, is roughly negative 38, negative 40. So if I saw that, then I know, okay, then that's a problem. I have a problem with my coolant temp sensor. But if I saw what it actually was, like say that at the coolant temp sensor, then I would suspect that there's a problem. It's not making it back, or there's a short to power because high is low, right? So if I see that at the coolant temp sensor, then I know there's an issue elsewhere going on, and I can trace my way back and figure it out where the problem lies. So we got to definitely check between the scanner data, which is process data, and the actual live data, raw data coming off of the vehicle in order to verify everything's working the way it should. Right? So that is our scanner versus scope chat. And with that, that's our time here today. So make sure you tune in for new diagnostic content every week. We'll be premiering a new video every Wednesday at 7 p.m. UK time, so make sure to check it out here on our YouTube channel. Please make sure you also subscribe, thumbs up, and ring that little notification bell so you'll know anytime we post new content. With that, time for questions. Now, if you have any questions, once again, if you're watching this on the premiere, just leave it in the live chat and we'll do our best to answer those. Otherwise, leave a comment under the video and we'll get to those as we monitor those comments as well. So I'd like to thank you for taking a little bit of time out of your day to learning a little bit more about how you might be able to be more efficient at diagnosing vehicles using some of the information that we've been giving you today. Hopefully we'll see you next week, and we'll see you on any of our other videos. Have a good week, have a good night, and take care.